Welcome to Sample Preparation and Light Recovery, analysis of efficient and environmentally friendly methods, presented by American Pharmaceutical Review and sponsored by Buki Corporation. My name is Elizabeth Thomas, editor of American Pharmaceutical Review, and I will be the moderator today. Before we begin, I'd like to remind our viewers that this event will hold a live question and answer session at the end of the presentation. You can submit a question at any time using the general chat box located at the bottom of your screen. Please notice that there are documents available for download in the Documents tab located at the bottom right-hand corner. Allow me to introduce today's presenters. Jeff Reed is Product Specialist for the Evaporation segment at Buki Corporation. In his role, Jeff specializes in benchtop, industrial, and parallel evaporation. Previously, he worked on the development of silica media for HPLC columns. Jeff has worked both in the analytical and preparative sides of the industry. Garrett Boone is a laboratory analyst at Eurofins Air Toxics. Garrett has laboratory experience as a GC, HPLC, GCMS, and extraction chemist with Eurofins Air Toxics. In his role, Garrett leads the production and processes for extractable methods, as well as testing and implementation of new technology in this area. At this time, I'd like to welcome our first presenter, Jeff Reed, to join the webinar. Welcome, Jeff.
First and foremost, I'd like to thank everybody for joining today's webinar. Today we're going to discuss ways you can perform labor-free, environmentally friendly concentrations. I'm going to start off with a quick overview of parallel evaporation, discuss the importance of solvent recovery, discuss ways how you can enhance your analyte recovery, go into ways to reduce labor costs, and then Garrett Boone from Eurofins is going to talk about common concentration methods. So what is parallel evaporation? So to define this, you have to think, what is distillation? Distillation is an overall process where you take a liquid to a vapor and then a vapor back to a liquid. Transforming a liquid to a vapor is known as evaporation. This is done with energy applied into a system, which is known as heat. To take the vapor back to the liquid, that is known as condensation, and you need energy out of the system in the form of coolant. You need the energy into the system and the energy out of the system to be equal to have an efficient overall distillation process. So what parallel evaporation is, it's evaporation of multiple samples at one given time. When performing parallel evaporation, it's always advantageous to use a vacuum source. The reason for this is because the boiling point depends strongly on the pressure. The lower the pressure, the lower the boiling point. What this means is you're pretty much manipulating the boiling point of a solvent by reducing the pressure of a system. This is advantageous for three reasons. One, you're going to protect your thermosensitive samples because you're using lower temperatures. Two, obviously you're going to increase your throughput. Three, you're going to eliminate nitrogen usage. The overall workflow in the environmental industry is shown here. You can see it starts with sample preparation. You actually prep up your sample. Then you extract your sample. Followed by the extraction step is the concentration step. And this is where it's always smart to go with parallel evaporation so you can concentrate multiple samples at one given time. This step is one of the most important steps, if not the most important step, because the next one is your analytical analysis. So you have to make sure you have an efficient concentrator that actually gives you high yields, high analyte recovery along with solvent recovery. So there's three different technologies out there for parallel evaporation. You have your nitrogen blowdown technology, your vortex evaporator technology, and your vacuum centrifugal technology. Nitrogen blowdown, what that does, you're utilizing hot nitrogen to evaporate off the solvent. The vortex evaporator and vacuum centrifuge, they utilize pressure. Also, if you look at these pictures, you see there's a solvent recovery source with the vortex evaporator and the vacuum centrifuge. You don't see it with the nitrogen blowdown technology because there's no sufficient way to collect your solvent. What's happening is that you're utilizing hot nitrogen, hitting the solvent to evaporate up, and there's nothing collecting the vapors. The vapors are pretty much passing through the fume hood and into the atmosphere. So you can see it's very bad for the atmosphere. It's not very environmentally friendly. And, you know, you're utilizing a lot of nitrogen to evaporate. You can see also with the vacuum centrifugal technology, the sample's held to the bottom of the glass vessel by centrifugal force. So you can imagine a centrifuge is very big, very expensive. So it's not really an ideal technology. My most ideal technology when performing parallel evaporation is always a vortex evaporator. And I'll explain why later on here. So an overview of a common vortex evaporator I have shown here. This is the Syncor. You can see there's a platform. This is where the heat is generated. Remember, that takes the vapors or the liquid to the vapor form. You have your rack and vacuum cover where the samples are held in parallel. You have your vacuum source, which generates the pressure inside the system. And then you have a primary and secondary solvent recovery source. This way you can collect up to 95% or if not higher of the evaporated solvent. And if you notice the secondary solvent recovery source, it's actually behind the vacuum pump. That's so if vapors do get pulled into the vacuum pump, they actually go out the exhaust and condense down the secondary condenser. That way you have absolutely no solvent vapors passing through the exhaust and going up the fume hood. So the main reason, the importance of the solvent recovery is what the EPA, the US EPA calls the Emissions Reduction Program. This here, I took the link from their site so you can look into it more if you want, but this quotation is taken from US EPA method 3500C, and it's on pretty much every concentration method out there where it states, a solvent recovery apparatus is recommended for use in evaporative concentrators. So what the EPA is saying is if you're performing parallel evaporation and you're concentrating your samples, you know, you have to abide by their regulations. If not, you have to deal with fines. So what they're saying is you have to sufficiently collect your evaporated solvent. You can't just let it pass through the fume hood. Another reason it's important to collect your solvent is because the dangers of the solvent. Most environmental companies out there, you're utilizing dichloromethane to extract your sample, and then you have to concentrate that down. Well, as everybody knows, dichloromethane is a chlorinated solvent. It is a carcinogen. So it's very dangerous for the user to work with this and have to breathe it in. So not only are you protecting the atmosphere and creating a more green chemistry, environmentally friendly atmosphere, you're also protecting your users that are performing the concentration inside the laboratories. So again, I have the Syncor shown here, and I'm showing you that there's two solvent recovery sources. This way, you're collecting up to 95% or if not higher of your solvent. So make sure if you're in the market for a vortex evaporator or a parallel evaporation unit, make sure you do your homework. Make sure you get one that utilizes pressure, that has sufficient solvent recovery system so you can abide by the US EPA. So ways to enhance your analyte recovery. Usually the most common way when you're done concentrating a sample, you take the vessel and you squirt down the sides of the glass wall. You do this with additional solvent, and it adds additional step to your process. So what we have here is what we call a flushback module. A flushback module is a cooling zone that goes in between the glass vessel. What this causes is the vapors that are being evaporated and passing through the flushback module, some of the vapors will actually condense back down and rinse the glass wall. So it's doing it automatically, and it's also using the solvent that's already being evaporated, so you're not using additional solvent. And this next slide, you can actually see how it works. You see there's a common concentration vessel with a sample in it, and you know you won't want to concentrate usually to 1 ml in that appendage. So you can see the evaporation process starts, the solvent vapors go up, some of them condense back down the side of the glass vessel and rinse the analyte back into the appendage. so you actually have a higher analyte recovery. Here's a picture showing how effective the flushback module is. The picture on the left, it does not have it didn't use a flushback module, so you see there's more buildup of analyte on the sides of the glass vessels. The vessel on the right did have a flushback module, and it's less analyte recovery, so you're going to have more analyte in that appendage. So again, what this is, it's a more automated way to actually increase analyte recovery by two ways. One, you're reducing labor costs because you're eliminating the step of actually rinsing the glass vessels down. Second, you're also eliminating extra solvent being used to wash down the vessels. Another way it reduces labor costs is one way to reduce labor costs is actually when you utilize pressure instead of nitrogen. Yes, there will be an upfront cost with the vacuum pump, but it pretty much, I'll show you a cost saving analysis where the vacuum pump is pretty much paid for within a year. So it's utilizing pressure is very, very advantageous for all environmental companies that are performing parallel evaporation. Here's the labor cost. I actually did this with an environmental company on the East Coast. This is very conservative. What I have shown here is that dichloromethane, 300 milliliters of dichloromethane, it takes about an hour to evaporate with nitrogen. Usually it requires about 3 liters. Now that's approximately, it might be 4 liters, it might be 2 liters, but on average it's about 3 liters. The cost of nitrogen for this customer was 30 cents per liter, and that's very conservative because it can cost you up to $1.50 per liter, but I figured let's be conservative with this cost analysis and stick with 30 cents. So in a day it's about $7, in a week $36, and 1 year it can run you up to about $1,900 being conservative, and that's pretty much the cost of a new vacuum pump. So again, if you want to reduce labor cost, eliminate nitrogen and utilize a vacuum source, which is usually done on vortex evaporators. Also, like I mentioned earlier, you're increasing the throughput. So what I have here is the throughput of different solvents that are used. You can see hexane using a vacuum source, it took about 5 minutes to evaporate. Toluene, it looks like it's about 12 minutes. Hec chem, about 6 minutes. Acetone hexane, about 5 minutes. And you can see the rest there. I'll keep that up for everybody. But this was done on a Syncor Vortex evaporator. And, you know, you could compare these rates to other technologies out there. And the bottom line is, again, utilizing pressure, you're actually going to really increase your throughput. Last way you can reduce labor cost is with what I like to call a gradient step down vacuum setting. So what this is it's an actual vacuum setting. So if you're evaporating dichloromethane, you don't want to just turn that vacuum pump to, let's say, 200 millibars, because most likely it's going to bump and contaminate other samples. You want to gradually bring that vacuum pump down to a set pressure. That way you equilibrate the pressure in the system. You don't have to worry about bumping. Well, you don't want to sit there and babysit the process. You want to just do it and then walk away. So what this vacuum pump and vacuum controller is, the V700 V855, it actually has a gradient function in it. So you can program these step-down pressure settings, hit start, walk away. The vacuum pump, when it's done, the last setting, it actually aerates itself and it goes back to atmospheric pressure. Then the sample that's been concentrated to, let's say, 1 milliliter is being safely held in the bottom of that appendage at atmospheric pressure. And that way you don't have to really be there when it's over. So if you go out to lunch or whatever it could be, your sample's still safe and still at the bottom of that appendage. Also, you can see that there's a F108 chiller here, which is it's actually very highly compatible with vortex evaporators. And what that unique thing about this system is that you can actually control the chiller via the vacuum controller. So it's more environmentally friendly in power savings, and it's a more efficient process. That's where we're moving to now, is to more efficient processes, more environmentally friendly processes. So at this time, we're going to jump into some polling questions. Let's see, the first polling question out there is going to be, what is the U.S. EPA's biggest concern? I'll give everybody about 30 seconds to answer this, but after listening to that presentation, what do you think their biggest concern is? Okay, so it sounds like you have solvent emissions, which is B, which is absolutely correct. New technology, the U.S. EPA is not worried about new technology. They're not worried about method development, although, as everybody out there knows, the methods can be developed more. But the main concern for them right now is solvent emissions, because major companies are emitting way too many chlorinated solvents into the atmosphere, and they're starting to find that it is becoming a problem for everyone. Okay, so the next question is going to be, let's pull it up here. How can you concentrate samples faster? I'll go over these: decreasing heating temperature, utilization of pressure, eliminate condensation of vapors, or all of the above. And again, I'll give everybody about 20 seconds, 30 seconds to answer this. Okay, so it looks like majority, 85% of the people picked utilize pressure. Yes, that is it. Some people picked all the above, and honestly, if it wasn't for A, you could say that, but that is how you do it. Obviously, if you decrease the heating temperature, you're actually going to decrease the throughput, because remember, energy is the energy applied into the system is heat. So the higher the energy, the higher the throughput. But utilizing pressure, again, it allows you to manipulate the boiling point of the solvent, and then you can use less energy. Okay, so last polling question. Let's see what we have here. What is the most efficient way to increase analyte recovery? Rinse the glass walls with additional solvent. Rinse down the glass walls with pre-existing solvent. Use very high heating temperatures. All of the above. And again, I give everybody about 30 seconds. Okay, so 95% of the people picked B, which is correct. A, yes, you can, increase analyte recovery by rinsing down the glass walls. But again, remember, that's a step that you do after you concentrate, and what you're doing is you're utilizing additional solvent, and you're adding another step in the overall workflow process. So if you actually rinse down the glass walls with the pre-existing solvent, you're saving on solvent, and also you're reducing labor costs because you eliminate the steps that you have to rinse down the glass walls. And remember, a common automated device that does this is the flushback module. So that's it for the polling questions. Everybody did a great job. At this point, I'm going to pass it on over to Garrett, who's going to talk about some common concentration methods.
Thank you. Today I'm going to talk about and focus on EPA method TO13A, which was originally published in 1989 for the determination of toxic organic compounds in ambient air. The TO13A list of compounds is made up of a select group of polycyclic aromatic hydrocarbons, also known as PAHs, and these compounds occur in oil, coal, and tar deposits and are also produced as byproducts of burning fuels. The reason these compounds have received increased attention in recent years in air pollution is studies have found that some of these compounds are highly carcinogenic or mutagenic. So as you can see here, this is a list of 19 PAHs listed as target compounds for this method. Of these compounds, the one of particular concern is benzoate pyrene, which is known to be particularly carcinogenic and is also found in cigarette smoke. So next, I'm going to go ahead and go over what we used to do as our traditional approach to TiO13 extraction, which is first and foremost, you have to extract the samples, typically by PFE or pressurized fluid extraction, and collect the extract in a collection vessel, typically using DCN. Next, you would transfer that extract to a Caderna Danish or KD with an attached concentrating tip. After transferring the sample to a KD, a Snyder column would be attached to control the rate of evaporation, and then the apparatus would be placed on a water bath. Next, the analyst would then have to monitor the evaporation to ensure correct water bath temperature is maintained and that the evaporation is proceeding smoothly. This step, depending on water bath temperature, could take 15 to 30 minutes to complete per sample. Another important point to note would be that the analyst also has to be present the entire step to ensure that the KD does not go dry, causing a loss of analyte recovery. After the sample volume is brought within the concentrator tip, the analyst would then transfer the sample to a nitrogen blowdown apparatus to bring the sample to the desired final volume. Now, this step not only requires a minimum of 1 hour to complete, the analyst is also required to stay once again to monitor the samples and ensure that they do not go dry, once again causing that loss of analyte recoveries. However, by utilizing the SynCord platform, which is what our lab has started to use, we are able to take the sample extract and in one step, concentrate the sample to the desired volume. We also utilize our PFE equipment we utilize the Buki E914 extractor, which allows us to save a further step and allows us to transfer the sample extract directly from the extraction process in the same collection vessel to the concentrator, being the SynCore, eliminating sample loss due to transfer. So there are many benefits to parallel evaporation that we've seen compared to traditional methods. The traditional method, as Jeff noted earlier, of concentrating TiO13 samples is both material and labor intensive, as you have to sit and watch the samples to ensure they do not go dry and cause a loss of analyte recovery, as well as using a large amount of nitrogen, which adds to your overhead costs of your lab to perform the evaporation. Another disadvantage of the traditional method is that since it is a nitrogen evaporation step, you lose all of the hazardous solvent to the environment and increases your solvent costs as well. However, by utilizing a parallel evaporation system, you can virtually eliminate some of the problems with these traditional approaches. The system allows you to process each sample with the identical set of parameters while eliminating the need to stay and watch the samples. It also allows for higher throughput as you can concentrate many samples simultaneously based on rack size of your parallel evaporator. The SynCore system also recovers the solvent that the traditional method loses to the environment by collecting it in the receiving flask shown earlier by Jeff, and allows the analyst to either safely dispose of the solvent properly or possibly reuse the solvent depending on your application. This minimizes the environmental impact and increases your lab safety due to decreasing solvent vapors. Here are the parameters that we have utilized for our TiO13 analysis using the parallel evaporation system by Buki. So we set our platform temperature, which is your water bath, to 40 degrees C, the vacuum cover itself to 55 C. We keep our coolant temperature at 10 C and our orbital rotation at 300. We perform a step down in pressure while keeping the temperature constant, as I mentioned, to bring our extract volume to a final volume of 1 mil in 62 minutes for 6 samples in the time it would have taken us for 1 sample using the nitrogen blowdown approach. The system also allows our analysts to leave the distillation process, as when the program finishes, as Jeff noted, the system returns to atmospheric pressure and the distillation stops, with your sample being held in that residual volume tip in the cooled zone of 10 degrees C, as we have it set, so that you do not lose any analytes, and the sample can then be aliquoted by the analysts at their convenience. Using this approach, we were able to achieve very high and consistent recovery of the PAHs I noted earlier. I would like to finish by summing up the many benefits we have seen in our lab using parallel evaporation. It has decreased our overhead by eliminating nitrogen use during our blowdown step. It has also drastically decreased our labor costs associated with TO13 extractions because it allows our analysts to perform other tasks during the process instead of being required to stay and watch the samples to ensure that they do not go dry. It has also decreased the amount of glassware our lab requires. As before, with our traditional approach, it required approximately 6 to 7 pieces of glassware per sample. Using this new system through Buki, we can use 1 piece of glassware per sample. It has also drastically increased our throughput, as we can quickly complete 6 samples at once compared to individually by our traditional approach. And finally, and perhaps most importantly for our lab, due to the ability to set the Buki, set the vacuum controller and program it to use a specific set of parameters, each sample undergoes the exact parameters, and we no longer see as much variation in recoveries based on human error or simply differences in blowdown techniques among analysts, as the system is simply loaded and then turned on using the program we have set to give extremely consistent results. Thank you again for your time.
Okay, thank you, Garrett. Thanks, Garrett. We will now begin the question and answer portion of the webinar. Our first question is for Jeff. Jeff, can you automate the evaporation process using the vacuum controller?
Well, Liz, yes. You have to make sure the vacuum controller has an aeration option, that it can self-aerate itself. You want to make sure it has some type of timer function, a gradient function of some kind, because what you're going to do is you're going to perform the process of time versus pressure. So depending on your starting volume of sample, let's say, again, it's 40 milliliters of dichloromethane, it could take you about 30 minutes. As long as you have a timer or gradient function in there, and the vacuum controller aerates itself to go back to atmospheric pressure, that's what you're doing. You're actually automating the process with it.
Okay, thanks, Jeff. The next question is, how can you eliminate cross-contamination when performing parallel evaporation? And Jeff, you can answer that one if possible.
Okay, so that's parallel evaporation. When you talk about parallel evaporation, a main concern that gets brought up is cross-contamination, because you're running multiple samples at one given time. If something happens, if there's bumping that occurs, you have to worry about that bumping of solvent of sample going into another vessel, which is known as cross-contamination. So one way to eliminate that is to use a system that has individual seals for each sample. So each sample vessel should have its own seal. So if there is something that occurs, some bumping that occurs, it's going to go through that seal and trap inside of a vacuum cover instead of cross-contaminating everything. Another way is, again, going back to that vacuum controller, make sure you have a vacuum controller that does have a gradient program. Remember, parallel evaporation, multiple samples, which means you're going to have less surface area in each sample vessel. So less surface area means there's more risk of bumping. So you need to gradually bring down the pressure of the system, and you want to do that with a vacuum controller that has a gradient function.
Okay, Jeff, isn't there a risk to lose volatile analytes when applying vacuum?
Well, when you apply vacuum to the system, as you know, semi-volatile compounds, they're harder to concentrate, but there's a risk. But that's why you gradually bring down the vacuum setting. You don't apply too much vacuum setting at one time to bring it right down to that mark, because then, yeah, you can blow out your samples. But if you gradually bring it down, the vacuum setting down, you eliminate that risk. There's a risk with all three of these technologies that I talked about: nitrogen blowdown, vortex evaporators, and centrifugal evaporators. There's a risk for all three of them. But I would say the least of the technology that has the least risk is the vortex evaporators, because you're gradually bringing down the pressure. And I mean, assuming you're gradually bringing down the pressure, you're going to have a lot less risk.
Jeff, to follow up on that as well, something we've seen on our end as far as volatile analytes, another way to minimize the risk that we have found to losing those analytes is by utilizing that flushback module that Jeff talked about earlier, as well as a very gentle decrease in pressure. That's really helped on our end to minimize that loss of those volatile analytes that are difficult to concentrate.
Okay, Jeff, why is it important to have an additional condenser after the pump?
Okay, so you want an additional condenser at the pump because what happens is that primary solvent source, that primary condenser, is going to condense most of that solvent. But again, remember, you're doing your extraction with dichloromethane, which is very volatile. So what happens at the end of the process, when you're getting the sample volume lower and lower and lower, you're taking a risk to re-evaporate the solvent that's already been evaporated, because remember, dichloromethane is very volatile. So what happens if that re-evaporates and goes to the vacuum pump, it has the risk of going out the exhaust. But having a secondary condenser behind the vacuum pump will actually make sure you collect all the solvent. And having two solvent recovery sources there, you're pretty much able to achieve a very, very high solvent recovery source. Again, you don't want the users breathing in chlorinated solvents, any solvents at that, and you definitely don't want these solvents passing through the fume hoods.
Jeff, what type of implementation and installation support does Buki provide to customers post-sale?
Well, pretty much we can work with companies that help them with their parameters. I've worked with many companies, environmental companies, over the past couple of years, and helped the users, with the installs, with the actual method development, and pretty much all the way until they're happy. I mean, Garrett was a very good customer of ours, and I enjoyed working with them. And I took probably about 2-3 trips over there to his facilities, and I pretty much help help him build the method and find his parameters. So we're a well-known company. We specialize in evaporation, so anything we can do to help our customers, we're willing to do.
Okay, what is the size of the footprint of the thin-core system?
Garrett, I'll answer that, Garrett. Let me just pull up some literature here. A lot of the information you guys can download from the internet, but I can give you exact size here in 1 second. Now, I've worked with a lot of systems over the past couple years, and I got to say, in general, you have nitrogen blowdown, which is pretty compact. Vortex evaporators are very compact, and then your centrifugal ones aren't as compact. The actual thin-core vortex evaporator It is, the width is 480 millimeters, the height is 354 millimeters, and the dimension, or the depth, is 487 millimeters. So put that in perspective. I would compare it to, it's really not that big. I mean, looking at it on our website, you really see you can fit quite a few. They don't need to be placed in a fume hood, but an average fume hood, you could probably put 2 or 3 in there. But again, something unique about a system that has solvent recovery is that they don't need to be in the fume hood. You can put them outside the fume hood because remember, you're actually collecting the solvent.
Okay, is there an advantage to using heated nitrogen rather than a warming water bath when using N2 evaporation?
Oh, very good question. Garrett, you have a lot of experience with nitrogen blowdown apparatuses. What do you think on this one?
Yeah, that is a really good question. For us here, we always use we never tried the warming water bath approach. I don't know if there would necessarily be an advantage to it, because really you're just transferring the heat you're introducing to your samples from the nitrogen to your solvent. So unfortunately, I have never tried that. But yeah, I would think there wouldn't necessarily be an advantage or a disadvantage. As I mentioned, you would just be essentially introducing the heat from a different source.
Yeah, I guess I've seen that in a lot, and I think, tell me if I'm wrong, Garrett, I think that water inside of nitrogen blowdown systems is to try to keep that solvent at a concentrated volume, so it's harder to overblow the sample. I don't know how effective it is, but you know what Garrett said, I would definitely. He's used those in the past, so he's a good resource for those.
Okay, this audience member is wondering if they can also evaporate to dryness using the Syncor.
Yes, so the Syncor, you have 2 options. You can concentrate to a residual volume of 1 ml, 3 mLs, or 0.3 mLs, or you can go to dryness. You know, it's a very flexible instrument. It's actually, you pretty much have your platform, which I showed you earlier, which generates the heat, and then there's multiple racks, multiple positions you can put on that platform. So if you did want to go to dryness, we have a rack especially for dryness. If you want to go to residual volume, we have a rack for residual volume. That way you don't have to, you know, purchase multiple instruments. You purchase one platform and then purchase multiple racks to suit your application, whether it's dryness or to a residual volume.
Garrett, this next question is for you. Are there disadvantages to evaporating acids up to 4N HCI in the enclosed systems?
We have not tried evaporating any acids in our parallel evaporator. The only disadvantage that I can think of at the reason we haven't tried it, we don't deal with the acid too often, but one disadvantage is those seals that Jeff talked about earlier would have a lot less of a lifespan if you were evaporating acid, so that could increase how often you would need to replace those seals, as the acid would eat up some of your parts in the equipment. That would be the biggest disadvantage to that I know of. Is there any other disadvantages you can think of, Jeff, on the Syncor specifically for acids?
Not really off the top of my head. I got to tell you, the main materials of contact is going to be borosilicate glass, which it has a fine compatibility rate, PTFE, which I have to actually, if you email me, you can get my information from this webinar. If you email me, I can look into it more. But I would just have to do a cross run of the materials and see the compatibility rate with them. So if you give me what acid and what % acid it is, I can see if it has a high compatibility rate with the materials, which I said is pretty much borosilicate glass, PTFE, and PFA. I mean, and all three of those are very, very high inert materials. So I want to say off the top of my head, no, but please email me so I can do further investigation on a certain acid and the percentage of that acid.
Jeff, what are the different types of vessel and rack sizes available for the Syncor?
Well, if you want to concentrate your samples, you have an option of a 4-position, 6-position, or 12-position. 12-position in each position, it can hold up to 120 milliliters of sample volume. The 4-position can hold up to 500 milliliters of in each position. Now, if you want to go to dryness, you have an option of a 4, 6, 12, also a 24, 48, or 96. So you can evaporate 96 samples at one given time. That's big if you're doing some type of flash chromatography and you need to dry down your fractions. A 96 rack would be perfect for that. But if that's the different sizes we do offer. So there's multiple racks, multiple different options you can do with the Syncor.
Garrett, you stated that you used a speed extractor for your extraction. What have you used previously, and how does this compare to the previous way of extraction?
Yeah, we do utilize a speed extractor now. It's still relatively new, but previously we mainly used the ACE3 and ACE4 systems by Dionix. A big difference that we have seen, essentially the way they work is identical. However, the speed extractor allows us to extract, the unit we have extract 4 samples simultaneously and in parallel, whereas on the ACE systems we were only able to do 1 at a time. So comparatively, the speed extractor has worked really well for us in the sense that we essentially have increased our throughput on our extraction by 4-fold, just in the fact that the speed extractor is able to do it in parallel, as well as the cells. I don't know if you're familiar with the ACE cells, but the ACE cells, you have to screw on the ends for each sample when you're prepping them. The Buki system doesn't have caps on the ends. It seals it on its own, which allows for a decrease in our analyst error, like not screwing a cap on all the way. The speed extractor also checks for leaks, and that's been a big factor for us to minimize the chance of losing samples in an extraction due to an unknown leak.
Okay, we have time for a couple more questions. Jeff, your early example involved using nitrogen to evaporate 300 milliliter of DCM. Is this the preferred method to evaporate such a large volume relative to rotavapor? And is this new product cheaper than using a rotavapor? This audience member comments that it seems simpler to use.
Oh, great question. Okay, so yeah, for your water samples, you have to extract with a higher volume of solvent, which is usually DCM. Yeah, I would honestly, if I did it my way, I would do the Rotavap, because you're not utilizing nitrogen and you're not just pumping nitrogen through the fume hood. Now, the only downside of a Rotavap versus a parallel evaporation unit is that Rotavaps you're doing 1 at a time instead of 6 or 12 at a time. So to evaporate that high of solvent, I would say your best bet is to use a Rotavap. I think that'll be more efficient than using hot nitrogen. But again, if you the new system, I think when they say the new system, I believe that you're referring to the Syncor. Yes, there's several benefits over a lot of the older technologies, and we went over a lot of those, whether it's solvent recovery, throughput, pressure, utilization of pressure, the flushback module. So I would recommend for that, maybe using a vortex evaporator that has a flush back module, smaller positions such as the R4, which can hold up to 500 milliliters of sample. So you can actually do 4 samples at one given time. So it's going to be much quicker than a rotovap, and it's going to allow you to sufficiently collect the solvent and not use nitrogen.
Okay, we have time for one more question. Can you recycle recovered solvents?
Oh, that's a great question. We're working with a couple customers. I'm working with a couple customers that are want to do that because there's a cost to dispose of the solvent. So if you're able to recover the solvent and then recycle it, that could save you a ton of money in 1 year alone. So can you? Yes. Now, I'm still working with these customers to see if they can actually implement it in their workflow. What do you think, Garrett? If you took your recovered solvent, do you think it would have a high enough grade for you to reuse it in your workflow?
Actually, that's something we are looking into at the moment. We haven't had a chance to really fully explore it yet. I believe it would be, based on our recoveries we get using the parallel evaporator, I believe it would be of a high enough grade to reuse. It's just a matter of testing that prior to using it. But based on our recoveries, the recollected solvent should be of a high enough grade to use in some form. And that is definitely something we're looking into doing because, like you mentioned, disposing of the solvent is extremely expensive, and if you can reuse that solvent multiple times, that's just saving your company money down the line. And so far, it looks like it wouldn't be too hard for us to introduce that to our workflow. Since it's all collected in one vessel, it would be really simple to transfer that to a different container or whatever you needed for your lab if you could recycle it. So, yeah, I think you could. It's just a matter of we haven't had a chance to really fully explore that yet.
Let me also comment, Liz. So pretty much what you would do after the recovered solvent, you would take that recovered solvent and you would want to put it on a bigger scale distillation unit to actually purify it even more. Now that purified solvent you can take and put back into the process. But there's different steps for you to purify it, whether it's an industrial rotary evaporator, a distillation unit. The question is how will you actually purify it? And is that purification instrument sufficient enough to reuse that solvent? Which honestly it is. It's just that we are still in the stage of actually proving it and showing it to the market.
Okay, we're going to allow one more question. Jeff, all things considered based on your presentation, does the SynCore system render N2 blowdown an obsolete method?
Well, nitrogen blowdown's been around a very long time, and it's still used today. I don't think it'll be obsolete. It depends on how far the emissions reduction program goes, and not just on that. The EPA, obviously they want you to collect solvents, so it's not so much nitrogen blowdown. There is some nitrogen blowdown systems that have a solvent recovery system. I've worked with a couple, and they had up to 75%, but it wasn't quite high enough. The bottom line is to make sure you look into a system that collects the solvent. If you're unsure of it, have the vendor prove it to you. Collects 95 or not higher % of the solvent, has sufficient analyte recovery, sufficient throughput, and I would say that's the best approach to take if you're in the market for a parallel evaporation instrument.
Okay, thanks, Jeff. Unfortunately, that's all the time we have. Any questions that we were not able to address here live will be answered via email. We'd like to thank our presenters, Jeff Reed and Garrett Boone, for sharing their knowledge with us, and also offer a special thank you to Buki Corporation for sponsoring today's event. Audiences can view this webinar on demand by visiting AmericanPharmaceuticalReview.com. Thanks, everyone.